Welcome everyone to section 1.2, Probability Theory of Casella and Berger's textbook Statistical Inference. Notice that section 1.2 is called Probability Theory, same as this chapter, which suggests that this section will cover a lot of the important stuff in this chapter. In particular, big picture, what we're going to do in this section is we're going to learn how to assign probabilities to events or sets. Recall that in the last section 1.1 on set theory, we looked at what events or sets are, and we looked at how to relate two sets, what it means for one set to be a subset of another, what it means for two sets to be equal, and then given a bunch of sets, we looked at how we can create new sets by using set operations such as intersection, union, and complementation. So now in this section, we will look at how we can assign probabilities to events. In the first subsection, 1.2.1, axiomatic foundations, we're just going to define what a probability function is. Then in subsection 1.2.2, the calculus of probabilities, we're going to look at some properties of the probability function. And in the last two subsections, counting and enumerating outcomes, we're just going to look at a particular case of a probability function that operates on a finite sample space and when the outcomes are equally likely. Okay, so that's the plan. The authors begin by introducing a few definitions. So they state that here somewhere they state the next page that a firm understanding of statistics requires at least a passing familiarity with the following. And then they define what a sigma algebra or a Borel field is. And then in particular, we pick a particular Borel field when the sample space is countable and when the sample space is uncountable. But I want to point out one thing that so we'll discuss that in a minute. But this example 1, 2, 3 here with picking a sigma algebra when the sample space is uncountable is not used anywhere else, in this section or in this chapter really. I mean, later it is used in this chapter, and so that's when I'll bring it up. But here it is just kind of introduced and not used, kind of like a writing a function in Python that you don't use. I don't think that it's worth introducing it here. So then we'll work with just the scenario in which we have a countable sample space. So just keep that in mind as a framework for what we're going to talk about in this section. Okay, so we want to define this probability function. We know that functions have domains, and we know what we're trying to accomplish. We're trying to assign a probability to each event. An event is a subset of a sample space. So then it seems logical to pick as the domain for our function the set of all subsets of the sample space. Of the sample space S. Okay, and so this term Borel field is introduced as a particular collection of sets which satisfies three conditions. Right, there was that the empty set has to be part of it, that it's closed under complementation, and it's closed under what did that say? Closed under countable unions. So for any particular sample space, there are many Borel fields, but we're only going to care about one. We're only going to care about the Borel field, the collection of subsets that is a Borel field, the one that is just the set of all subsets. So when the sample space is countable, we're going to take this to be the Borel field, and is denoted by this cursive capital B. It's just the set of all possible subsets of the sample space. Okay, so this will be the domain of our probability function, right? And what the probability function will spit out will be numbers. But what is going to make those numbers be legitimate probabilities? So they will be legitimate probabilities if this is not just any function, but if it's a probability function. Okay, so that's the object of interest, a probability function. So let's define that. So given a sample space S and an associated Borel field B, a probability function which we'll denote by capital P, with domain being the Borel field, is any function that satisfies the following three axioms, which are known as axioms of probability or Kolmogorov's axioms. The first one says that the probability of A is greater than or equal to 0 for any event for all A that are elements of the Borel field. So all that says is that for any event A that we pick, any event you pick is going to be an element of the Borel field, right? Because the Borel field contains all the possible events, all the possible subsets of the sample space. So any event you pick, its probability needs to be non-negative. That's the first axiom. Second axiom says that the probability of the entire sample space must be 1. That one is quite trivial. And the third one says that if we had sets A1, A2, and so forth that are all elements of the Borel field, and if they're all pairwise disjoint, then the probability of the union of these sets, and we can take the infinite union here, so if we have infinitely many sets AI, must equal the sum, the infinite sum of the probabilities. Okay, so this third one is very important, and it will be really, if you boil it down, it will be at the heart of everything we will do in this section. And not only next section, it's also going to play a very key role. Okay, so we've defined what a probability function is. So now if somebody gives us a candidate function, f, we check to see if the candidate function f satisfies these three axioms. And if it does, then this candidate function f is a probability function, which means that the numbers that it will produce will be legitimate probabilities. If we have another candidate function g, and this function g does not satisfy these three axioms, then it's a function, but it's not a probability function. And that means that the numbers that it will produce will not be legitimate probabilities. Okay, so when asked what's a probability, with this axiomatic approach, we're kind of kicking the can down the road, and we're saying, well, probability is what comes out of a probability function. And then sort of the discussion we want to have is about which functions are probability functions and which are not. Okay, so that's the approach. So now let's have one of these candidate functions, and let's think about whether it is actually a probability function or not. So let's take a very simple example. with a very simple sample space. So we're just flipping a coin. So then the possible outcomes are heads and tails. The associated Borel field consists of all the possible subsets. The empty set is included because an empty set is a subset of any set. H by itself is a subset of the sample space. T by itself is a subset. And then the sample space itself is a subset of itself. So there are four subsets that are included in the Borel field. Okay, so now we want to come up with some sort of candidate function. So let's say that we have a function f which assigns to the empty set 0, it assigns to h 0.3, and it assigns to t the number 0.5, and then it assigns to the set ht probability, well, the number of 1, not a probability, number. So we just have a function, it assigns numbers to all the subsets of the sample space, and now we want to see if this function f is a probability function. Well, let's check to see if it satisfies the axioms. Axiom 1 says that the probability of every event must be non-negative. Is this function assigning non-negative values? Yes, 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 yes. Okay, so axiom 1 is satisfied. Axiom 2 says that the probability of the entire sample space, in other words, this function must assign to the sample space the number 1. Well, here's the sample space, right? And so what is it assigning to the sample space? 1. Okay, so axiom 2 is also satisfied. So we got both of these satisfied. Okay, now the third one. Okay, so to check this one, we need to find all the possible pairwise disjoint sets and see if the probability of their union satisfies this equality. Okay, so what are all the possible pairwise disjoint sets? So we could take the empty set and the entire sample space. These are disjoint, they're pairwise disjoint. When we have two sets, we don't need to use the word pairwise disjoint. In the next section, I will expand on that. We could take the empty set also in combination with H. Those two are also pairwise disjoint, where the empty set is disjoint with when combined with any other set. Okay, and also H and T. Right, those two are also disjoint. Okay, so now we want to study their union. In particular, we want to study the probability of their union, because axiom 3 above says that the probability of their union must obey this equality here, and it must equal the sum of the individual probabilities. So we want to check if that is equal to the probability of the empty set plus the probability of the set H and T. For the second one, we'll want to check that it equals, again, the sum of the individual probabilities. Just write these out. For the third one, we want to check that it equals this sum. And then for the fourth one, we want to check that it equals this sum over here. Okay, so let's check. So what do we have here on the left? Empty set unioned with the sample space is just the sample space. And what's the probability of the sample space? Or what number does it assign to the sample space? 1. Okay, so we'll have a 1 here on the left. This expression on the left evaluates to 1. What about on the right? What's the probability of the empty set? So what is assigned to the empty set? 0. Okay, so this is a 0. And then what's the probability of this, of the sample space? That's a 1. So is 1 equal to 0 plus 1? Yes. So this first equality is satisfied. So the axiom 3 is satisfied for these two sets, empty set and sample space. Okay, let's look at the next one. We can do this a little faster now that we understand how it works. What's on the left is just h. What number is assigned to h? 0.3. What about on the right? Well, this is a 0. And what is assigned to h? Well, that's 0.3. Is 0.3 equal to 0.0.3? Yes. And you can probably see that the next one would also be satisfied, right? Because this is just 0.5, and then this is 0, and this is 0.5, and so this third one is also satisfied. Now what about the fourth one? What's this union? It's the sample space. What do we assign to it? 1. What about on the right side? What do we assign to h? 0.3. And what do we assign to t? 0.5. Is 1 equal to 0.8? No. So we have found two pairwise disjoint sets, h and t, for which axiom 3 is not satisfied. Therefore, axiom 3 is not satisfied for this function f, and therefore this function f is not a probability function. And we picked a very simple sample space here, and yet there was so much work involved. This definition of probability in terms of the axioms, it's great, it works, but it's very tedious given a candidate function to check if the function is a probability function or not, if the axioms are satisfied. So no wonder then that we have an easier way to build up a function and check whether it's a probability function. So we have an easier way to build up a probability function. So let's look at that. That's done in theorem 126. So theorem 126 says, let S be the sample space that consists of elementary outcomes S1, S2, and so forth up to Sn. And so it's a finite set, so we're picking a finite sample space. And then this capital cursive beta stands for the Borel field, or the sigma algebra, corresponding to this sample space, okay? And then if we pick for each elementary outcome probabilities, well, numbers at this point, lowercase p1, p2, and so on, up to pn, and if we pick each of these to be greater than or equal to 0, and if we make sure that these numbers add up to 1, then for any event A, element of the Borel field, we will define the probability of A to be what? So let's think about it for a minute. If we were to let's think of this example as one of rolling a die. We know there's 6 possible outcomes. So this is our sample space, and it's finite. So just like this theorem here is asking us to consider. Okay, and then suppose that there's an event of interest, A, which consists of these outcomes, 2, 3, and 4. So look at axiom 3 above. It talks about what happens to the probability of the union of pairwise disjoint sets. Now, the thing about elementary outcomes 1, 2, 3, 4, 5, 6, the elementary outcomes are by definition pairwise disjoint. Therefore, this event A over here, which consists of outcomes 2, 3, 4, can be written as the union of 3 pairwise disjoint sets. And in fact, any event can be written as the union of pairwise disjoint sets where the sets are elementary outcomes, because the elementary outcomes are pairwise disjoint by definition. Okay, so then in this definition, we're going to take the probability of any event A to be the sum of the probabilities where this is summed over all I such that the elementary outcome Si is an element of the event A. So in other words, the probability of event A will be taken to be the sum of the probabilities of the elementary outcomes contained in the set A. Okay, so the claim is then that if we define a probability function this way from the ground up, we build it from the probabilities of the elementary outcomes, that it will satisfy the 3 axioms and that it will be a valid probability function. And it's not that hard to see that it would. So notice that we required each of these numbers p1 through pn to be greater than or equal to 0, and that looks a lot like that, like axiom 1, right? Although here we're specifying the probabilities only for the outcomes, but the axiom is asking that the probability of any event is greater than or equal to 0. So there's that distance in our minds that we need to still keep. Okay, and then we've asked that these numbers add up to 1. So the sum of the probability of each outcome must be 1, and that this one maps exactly to this axiom 2. Okay, so there's that component of it. And then, axiom 3 works on pairwise disjoint sets, and what we're doing here is we're decomposing an event into its constituent elementary outcomes, which are pairwise disjoint by definition. So so then you can see that kind of that axiom 3 in spirit here as we're building it from the ground up, by taking the probability of unions of outcomes which are pairwise disjoint by definition. Okay, so now if we so now when we build the probability function this way, we don't need to check that it satisfies the axioms because we're told that it will. So now it's much easier to find probability functions. So let's go back to our simple example of tossing a coin, a sample space of consisting of just H and T, heads and tails. So if we let this be P1 and this P2, and if we assigned P1 a value of 0.2 and pH a value of 0.8, we've assigned non-negative values. We've assigned values that add up to 1. Therefore now we could build up the probability of any event of interest using this formula, and we'll have a legitimate probability function. And we could have picked other values, perhaps, so this was maybe a function f. We could pick another function that assigns 0.3 to P1 to h heads and 0.7, and you can see that it will satisfy all the conditions. Therefore from it we can build a valid probability function, and we could take another function h here which will assign 0.5 to the two outcomes, and that's just a special case. Right, there's just a particular case. There's nothing different about the situation in which the outcomes are equally likely. That's it for subsection 1.2.1, axiomatic foundations. Next we'll move to 1.2.2, the calculus of probabilities. Okay, in this subsection 1.2.2, the calculus of probabilities, we'll want to think for a second about how it is that people have come up with these three axioms of probability. So the process must have looked as follows. There was an entire pool of knowledge about probability functions. So if we, they knew that if a function is a probability function, all these, 1,000 different things are immediately true about that function because they're properties of probability function. But that entire pool of knowledge has been compressed and distilled into these three axioms, which are very minimalistic, and that's because that's how we define a probability function. So now if you have a function and you want to check that it is indeed a probability function, you have only three things to check as opposed to thousands. But as we're now trying to build in our minds what we should connote with the word probability function, we need to unpack these axioms and see all those properties of probability functions. And we'll start doing that in theorem with theorem 1.2.8. So in theorem 1.2.8, we're told that P is a probability function and A is any set in the Borel field. And in part A, we're asked to show that the probability of the empty set is 0. In part B, we're asked to show that the probability of the set A, an arbitrary set, must be less than or equal to 1. And in part C, we're asked to show that the probability of the complement of A is equal to 1 minus the probability of A. Okay, so let's start with the first one. So we want to show that the probability of the empty set is 0. So how do we do that? Well, currently we just know that P is a probability function, therefore the three axioms above must be satisfied. And here we want to somehow involve the empty set, and axiom 3, which is really the only meaty one, says that we need to work with pairwise disjoint sets, and we know that the empty set and the sample space are pairwise disjoint. Oh, and their union is the entire sample space. We know that probability is 1. Okay, so that looks promising, right? So then we take the empty set and the sample space, and we explore their union. So what is the probability of the empty set unioned with the sample space? Because the empty set and the sample space are disjoint, pairwise disjoint, then this axiom 3 applies. So the probability of their union can be written as the sum of the individual probabilities. Okay, and then what is the empty set unioned with the sample space? Well, that's just the sample space. So what we have here is the probability of the sample space equals the probability of the empty set plus the probability of the sample space. So then we can isolate the probability of the empty set to the right side, and on the left we have probability of the sample space minus probability of the sample space, and that is 0, and that's what we've been trying to show. Okay, so we found two disjoint sets, and we explored the probability of their union and used axiom 3. Okay, so part A is done. Let's take a look at part B. So in part B, we're asked to show that the probability of a set A, an arbitrary set, must be less than or equal to 1. Let's take a sample space and remind ourselves that if A represents the set of elements inside the circle A, then what's outside of circle A and inside the sample space is the complement of A. And A and the complement of A are disjoint by definition, and their union is the sample space. Okay, so that again looks promising and very similar to what we just did. So then we'll study here A and the complement of A. In particular, we want to look at their union. In particular, we want to look at the probability of their union, because by axiom 3, because these sets are disjoint, we know that the probability of their union can be written as the sum of the individual probabilities, and we'll do just that. And now, what is A union of the complement of A? Oh, that's the sample space. And so we have the probability of sample space on the left is equal to probability of A plus the probability of the complement of A. And by axiom 2, we know that the probability of the sample space is 1, right? So then I'll write that. And we're looking to isolate probability of A to one side. So let's do that. So we have probability of A is equal to 1 minus probability of the complement of A. And what is the complement of A? It's some event. And we're told by axiom 1 that the probability of any event must be greater than or equal to 0. So this number here is greater than or equal to 0. So if we subtract from 1 a number that's greater than or equal to 0, then we get a number that must be less than or equal, from this side it will be written this way, less than or equal to 1. Right, again, we're subtracting from 1 a number that's greater than or equal to 0, so then we get a number that will be less than or equal to 1. Okay, that looks right. So we are done then with part B. Okay, now in part C, we're asked to show that the probability of the complement of A equals 1 minus probability of A. But notice that we've actually inadvertently already kind of showed that, although we isolate the probability of A here to one side. But if we go up one row here, we see that here we can isolate the probability of the complement of A to one side, and then we get 1 minus the probability of A. And we are done, kind of by good fortune in this case, and that's it. Okay, so what have we shown? Let's just take a moment to think about it. So if we're told that we have a probability function P, immediately all we know is only the fact that these three axioms here must be satisfied. That's it. But we've just shown that these other conditions A, B, C are also satisfied by any probability function P. So, you know, we've expanded now our knowledge in our mind of what we know when we know that a function is a probability function. And let's keep doing that. So in theorem 129, we're asked to show some another 3 properties which are a little more complicated and a little more interesting to study. So in theorem 129, in part A, we're asked to show that the probability of the intersection of B and the complement of A is equal to the probability of B minus the probability of A intersection B. Okay, in part B, let's just take this one at a time. So, okay, so this is what we're trying to show in part A. Okay, so let's stare at these for a moment. What do we see here? A intersection B, and there's this set. So let's see if a sample space helps us see more here. So we must have some sets A and B. So we got A and B. So we know that this right here is A intersection B. Okay. And okay, what is this here? B intersection with the complement of A. So that refers to the elements that are in B but not in A. Okay, so notice that it is these elements here. These are the ones that are in B and not in A. Okay, so that's B intersection with the complement of A. Okay, and so notice that what we've really done is we've partitioned B, I should say split B into 2 sets that are disjoint. Very nice. And so then theorem axiom 3 applies. Okay, so then the 2 sets that we want to study here are A intersection B and B intersection with the complement of A. And we have seen that their union is just B. Not only that, but these guys are disjoint. Therefore, the probability of their union can be written as the sum of the individual probabilities, right, by axiom 3. And you see that we're pretty much done. We just need to isolate B intersection with the complement of A to one side. And then on the other side we have probability of B minus probability of A intersection B. And now we are done. Okay, so that was part A. So how do we do it? I mean, we're asked about some identity here, and we looked at these sets that are included in this identity, and we realized that they are disjoint by definition, and that their union is set B, and so that unraveled this exercise. Okay, let's look at part B now. So part B is tricky. Especially it's even trickier had we not done part A just now. But the authors have very strategically kind of arranged these exercises in the order that they did. So we want to show that the probability of the union of 2 sets is equal to the probability of the first one plus the probability of the second one minus the probability of their intersection. So notice that so let's go back. So we know that P is a probability function. Therefore, the 3 axioms are satisfied. And axiom 3 tells us what the probability of A union B is, but only if A and B are pairwise disjoint. So if they're disjoint, then we know that we can write that as just the probability of A plus probability of B. Okay, but what if they're not disjoint? Well, the axioms don't tell us anything about that, and that's exactly what we're exploring in this part B, because here we're not told that A and B are disjoint. A and B are just two sets. They can be disjoint or not. Okay, so how do we show this? Again, this one is a little tricky. It's not so clear where we should begin. So if we draw a sample space, I think that the approach I'll describe, which is the one described in the book, I think it would take quite a bit of time of staring at these and trying different things which would not work before we arrive at the solution. So I don't want to present it as anything simple. It's not, but the idea is to notice that we can decompose the union of A and B into two disjoint sets. So we start by saying, okay, A union B is what we're studying, and let's take A first, and then we want to union it with something that is disjoint from A. So what is that then? What's left over here? Well, those are elements that are in B but not in A. So that means those are elements that are in B but not in A. So those are elements in the set B intersection with the complement of A. Okay, and now these guys are disjoint, so axiom 3 will apply. Okay, so then we can study the probability of the two sides here, and the probability of what we have here on the right side is the probability of the union of two disjoint sets. Therefore, by axiom 3 we can write it as the sum of the individual probabilities Okay, so that's looking interesting. We have the probability of A union B, and we want to have that. We have the probability of A, we want to have that, but then we got this term here. Instead, what we want is that difference. But notice that it's just by good fortune, because the authors tried to make our life easy. We just solved what the probability of the intersection of B with the complement of A is, and it is in fact exactly that which we're looking for. So I'm just going to then replace, basically plug this in here. So what do we get? I'll write it over here, is that the probability of A union B is equal to the probability of A plus, instead of this, I'll write this expression here, and that's probability of B minus the probability of A intersection B. Okay, and that's exactly what we've been trying to show. Okay, so kind of creative, right? That we looked at the union of two sets and we decomposed it as the union of two sets that are disjoint. Okay, so that's part B. And now in part C, we want to look at what happens. So if we know that A is a subset of B, what do we know about their probabilities? And in particular, there's a claim that if A is a subset of B, then the probability of A must be less than or equal to the probability of B. Okay, so how can we do that? Let's draw a Venn diagram here. With sample space, we got A representing the points inside this circle, and then we want A to be inside of B because A is a subset of B. And we want to somehow get to where an expression about probability of A and B. So notice that we can decompose B into this set A and then this other set here, and their union would be B. So what are these two sets? Well, the first one's A, and then what's this other set here? Well, those are the elements that are in B but not in A. So B intersection of the complement of A. Okay, and their union is B. Okay, and these sets A and B intersection of the complement of A are disjoint. Okay, so then axiom 3 applies, so we can take the probability of both sides. And here on the left side, the probability of the union of two disjoint sets by axiom 3 is just the sum of the individual probabilities. So this is what we have. And so we want some sort of expression with probability of A to the left side. Okay, so let's isolate that on one side. Then to the right we have probability of B minus the probability of B intersection with the complement of A. Okay, and then what is this set here? Well, it's an event. It's a set. And by axiom 1, the probability of any event is greater than or equal to 0. So this here is greater than or equal to 0. So if we subtract from the probability of B something that is greater than or equal to 0, then we will get something that is less than or equal to the probability of B. Okay? And that's what we've been trying to show in part C. Okay, so we are done now with theorem 129. And next is just kind of an interesting observation on our result in part B. So let's look at that briefly, and that observation will have a name of Bonferroni inequality. So with the Bonferroni inequality, we're interested in studying what the probability of the intersection of two arbitrary sets looks like. So then let's isolate that probability of A intersection B. So we're taking it to the left side. Then what we have on the right is probability of A plus probability of B minus the probability of A union B. Okay, and what do we what do we want to study here? So this probability, so A union B is just an event, any event, and the probability of any event we've just shown in theorem 1 to 8. Probability of any event A, we've shown in 1 to 8 that is less than or equal to 1. So if we gave this the max probability of 1, then the probability of A intersection B would have to be greater than or equal to that, right? Because we've given this probability that is subtracted here the max value. So then we can write it as probability of A plus probability of B minus 1. Okay, so when the so now if you're you're playing a game, somebody tells you, okay, I got two events, and the probability of event A is 0.9. The probability of event B is 0.8, and let's say the probability of the intersection of A and B is 0.2. can that be the case? So you could use the Bonferroni inequality to say, well, let's see, the probability for any two events A and B, probability of their intersection, must be greater or equal to the sum of the individual probabilities minus 1, and that's 0.9 plus 0.8 and then minus 1. So and we get 1.7 minus 1, and that's 0.7. So we just worked out here that the probability of the intersection of A and B must be at least so I can put this inequality here as well, must be at least 0.7. So probability of intersection of 0.2 is not consistent with these two individual probabilities. If instead we picked probabilities that are very small values for A and B, instead of 0.9, if we picked a probability of 0.2, and instead of 0.8, we picked a probability of 0.3, and we try to apply the Bonferroni inequality. So what would it tell us in that case? That the probability of A intersection B must be greater than or equal to 0.2 plus 0.3 minus 1, and that's minus 0.5. Okay, so we know this is an event. The probability of any event is going to be greater than or equal to 0. We're told that by axiom 1. So this is not interesting. It's not incorrect. It's just that it doesn't say anything to us, right? We already knew that because we know even more. We know that the probability of any event is greater than or equal to 0. So the Bonferroni inequality only has teeth when the individual probabilities are large. Otherwise, it tells us something that is trivial. Okay. So then let's look at theorem 1 to 11 next. Okay, so we're given that P is a probability function, okay, and we want to show that the probability of A, any event A, can be written as the sum, the infinite sum of probability of A intersection with Ci for any partition C1, C2, and so forth. So recall what a partition is. A partition is a collection of sets that are pairwise disjoint, so no two of them have any elements in common, and their union is the sample space. Okay, so I think a little picture here of the sample space will help. So let's draw a partition, and I'll just draw it consisting of maybe these 6 sets here. So C1, C2, C3, C4, C5, and C6. And then let's pick our set A. So let's say that this is A. It consists of the points inside this yellow circle. Okay, so and then let's look at what A intersection with each set here is. So A intersection with C1 is what? Is the empty set. There's nothing at the intersection of C1 and A. Okay. What about A intersection with C2? There is this bit here. Okay. So that's A intersection C2. Okay, what about A intersection with C3? It's this part here. Okay, and A intersection with C4. It's this part. A intersection with C5 is this bit here. And A intersection with C6 is this part here at the bottom. So notice that A intersection with C1, A intersection with C2, A intersection with C3, so forth. All these sets are pairwise disjoint. No two of them have any elements in common, and their union is A. So we'll write that. A is equal to, well, the union of all these guys. Okay, now we can take the probability of both sides, and now on the right side we're taking the probability of the union of pairwise disjoint sets. So this axiom 3 applies, and so we can write it then as the sum of these individual probabilities. And so on. I'll just shorten it, and the last one is going to be the probability of A intersection with C6. Okay, and okay, and then so we could just write this with the summation sign, right? We could say that this is the sum as I goes from 1 to 6 of the probability of A intersection with Ci. So that's what we've shown with 6 sets. And there's nothing different when we go from this example with a partition of 6 sets to one that has infinitely many sets. So this 6 here can be replaced with infinity. We just need to do that everywhere here. And so here dot dot dot. So that looks right? We replaced it everywhere. Yep, so then what we obtained here is exactly what we were looking to show. Okay. Okay, so that's part A of theorem 1 to 11. And now let's look at part B. So in part B, we're going to prove Bool's inequality. And a little bit later, we'll see that the Bool's inequality is actually very closely connected to the Bonferroni inequality that we have just looked at. But let's take these one at a time. So part B of theorem 1 to 11, we want to show that, I'll need a little bit more space. We want to show that the probability of the infinite union of sets AI, as I goes from 1 to infinity, is less than or equal to the sum, the infinite sum of P of AI for any sets A1, A2, so forth. Okay, so again, let's take a step back. So we're told P is a probability function. We have sets A1, A2, and so forth, which are just any sets out there. We don't know anything about them. And the claim is the probability of the union of these sets, the infinite union, is less than or equal than the infinite sum of the individual probabilities. Okay, so so how do we show that? So this one, you know, the approach here is brilliant. It's nothing short of brilliant. You know, there's this introductory material that is presented here, and then, you know, in the midst of it, there's this result, which, you know, again, it really is nothing short of brilliant. But here's probably how they came up with it. So what we have on the left here is the probability of the union of a bunch of sets AI, and we don't know anything about these sets AI. In particular, we don't know that they are pairwise disjoint, but we'd like them to be, or we'd like to have sets that are pairwise disjoint, because that's when that axiom 3 applies. So so what the approach here is the following. They're saying, okay, well, you know, if we have a bunch of sets, let's take these sets here, let's call them A1, A2, A3, and A4. They're saying, well, let's create sets that are pairwise disjoint. So we'll create A1 star to be equal to A1. Okay, and I'll start coloring here what these starred sets are. Okay, so A1 star accounts for A1, so we got that covered. A2 star, they're saying, let's take that to be A2 minus, so we're going to exclude from it the set A1. And the authors really haven't introduced the set, the minus, the set exclusion operator, so let's quickly introduce it. So if we have sets A2 and A1, we can introduce what it means to exclude from set A2 the set A1. Well, that will be the set of elements little x, such that x is an element of A2, and x must not be an element of A1. So that's the definition. And notice that while the operator is new, the concept of set exclusion is not. We've already been thinking about it all along. So if we had here set A2 and set A1, and we were interested in this set here, which is A2 minus A1, what we've done up to now, right, we said, well, what are those points? Well, those are the points that are in A2 but not in A1, so we've been referring to that as A2 intersection with the complement of A1. And that's exactly what this is. It's A2 intersection with the complement of A1. So this set operator is new, but the set of interest, the resulting set, is not new. We've been looking at it all along. Okay, so so we want to let A2 star represent the elements that are in A2 but not in A1. Okay, so let's see what those look like here in our sample space. So here are the elements that are in A2 but not in A1. Okay, and then they're saying, okay, well, let's keep going and let's let A3 star stand for the set consisting of the elements that are in A3 but not in the union of the sets with lower indices. So from A3, we're excluding the elements that are in the union of sets with lower indices. Those are 1 and 2 in this case. So in the picture, what does that look like? Well, we're looking for the elements that are in A3 but not in A1 or A2. Okay, so there they are. And so you see now the idea. So A4 will consist of, let's write that one out as well. A4 star will consist of the elements of A4 minus elements that are in the union of A1, A2, and A3. And so in the picture, it's the elements that are in A4, but not in the other ones. Okay, so what have we accomplished? Well, a lot, but some of it is not even obvious yet. But what we've already accomplished is we have shown by construction that the infinite union of the sets AI is equal to the infinite union of the sets AI star. And we prefer these sets AI star because these are pairwise disjoint. So great, so now axiom 3 applies, and so we can write, well, now we're going to take the probability of this expression. So the probability of the infinite union of the sets AI star by axiom 3 can be written as the sum of the individual probabilities. And that's kind of nice. You know, that's what we've been trying to show. But the reason I said that what we've accomplished with this construction is kind of more than meets the eye is that, okay, well, we've applied axiom 3, and you know, so what? Like, how do we go now from here, you know, the sum of these sets that we just came up with to what we're trying to show? If you know, if so far kind of we've built these sets AI with the only intention being, you know, that you know, we would like this construction just because their union is, just because these sets are disjoint and their unions are equal, and the union of the AIs and the union of the AI stars, then you know, there would be no path forward from here. But what now becomes obvious, and that's the brilliant step, is that when they've come up with these AI star sets, they not only realize that these sets are pairwise disjoint and their union is the same as the union of the AI sets, but they also realize that by design a set AI star is a subset of AI, and that is brilliant, because we have shown in theorem 129 part C that if A is a subset of B, then the probability of A must be less than or equal to the probability of B. Therefore here the probability of AI star must be less than or equal than the probability of AI. And you see why, right? You see why the probability of you see why AI stars are subsets of AI. I mean, we can go back to, you know, the construction. So A1 star is chosen to be A1. So yeah, A1 star is a subset, or you know, A1 star is a subset of A1. They're equal. That works. In the second case here, we have A2 star is set equal to the set A2 after we exclude from it another set. So A2 star will definitely be a subset of A2, and A3 you know, as well, and so on. And you know, I've never written kind of the generic formula here, but I spelled it out. It said that, you know, AI star equals AI. From it we exclude the union of all the sets AI with lower indices. Okay, so that's brilliant, that AI star is a subset of AI, because now we said that this must be true here. Probability of AI star must be less than or equal to probability of AI, and that's it, because then we can write this as this infinite summation is less than or equal than the infinite sum of the probability of AI. And that's what we've been trying to show. So we're done. Very nice, very neat approach that we should keep in mind and kind of learn from. And so one last thing here is so this is known as the Bool's inequality. Bool's inequality. So now there's a claim that if we plugged, instead of AI, the complement of AI, that we'll get to a more general expression of the Bonferroni inequality. Okay, so let's quickly explore that. Well, there's this claim that this Bool's inequality is very closely related to the Bonferroni inequality. In particular, we're told that if we just applied the Bool's inequality to the complement of AI instead of AI, that we would get a generic form of the Bonferroni inequality. And let's remind ourselves just quickly what the Bonferroni inequality was. Bonferroni inequality. So that one was a statement about the intersection of two sets. It said that the probability of A intersection B is always greater than or equal than the probability of A plus the probability of B minus 1. Okay, so well, let's see if we can make sense of that. Okay, so I've plugged here the complement of AI instead of AI, and so let's see what the Bool's inequality tells us. So it says that it's less than or equal than the infinite sum of the individual probabilities, which here are the complement of AI instead of AI. Okay, so that's what we know. Okay, and so let's just look at this set here for a moment. So this union of the complements of AI. So this union, infinite union. So one thing though, although so the claim is that we can apply the Bool's inequality to the complement of AI, but we want to take this over not an infinite number of such sets AI, but a finite, particular n set, a number n of such sets AI. Okay, so let's study what this union here is. So we have the union as I goes from 1 to n of the sets complement of AI. So we could write out what that means. We have the complement of A1 union with the complement of A2 union with complement of A3, and so forth. Now, where have we seen this before? You might recall in section 1.1 we looked at De Morgan's laws. De Morgan's laws. And there were two there. So if you recall, we had one where we had a chain held by unions, and we took the complement of this set. Well, we've shown that what we get then is we take the complement of each set, and these are held together by the operator other than the one inside the parentheses, so it'll be the intersection. And then there's another form for when we have intersections chaining these sets inside the parentheses. And then same principle, we take the complement of each, and these are held together by the operator other than the one holding that chain together, so it will be the union. Okay, so which of these two looks like it would apply in our case here? Well, we have here a chain held together, a chain of the complement of sets AI held together by unions, so that looks a lot like what we have here. So then we could write this here as A1 intersection with A2 intersection and so forth, and we take the complement of that, right? Okay, yes, that looks right. Okay, so let me then make a little room here at the bottom. So we've just looked at sets. Now let's look at the probability of these sets. So now we have the probability of this set. So I'll just write it out. The probability of the set here on the right, which is A1 intersection with A2 intersection so on, intersection with AN. And now it's this is the set, is the complement of this set. Okay, so we have the probability of the complement of this set is less than or equal than the sum, so it goes from 1 to n of the probability of the complement of AI. Okay, so that looks good. Now we have shown in theorem 128 in part C that the probability of the complement of A is equal to 1 minus the probability of A. And we'll want to apply this here 2 times. So notice that what we have here inside the, well, it's the probability of the complement of a set. So we'll just write it as 1 minus the probability of that set. A1 intersection with A2, intersection so on, intersection with AN. And that must be less than or equal than the summation as I goes from 1 to n, and instead of the probability of the complement of AI, we'll write 1 minus the probability of AI. Okay. So, you know, what's the destination here again? It's easy to forget what we're trying to get to, but the Bonferroni inequality was an expression about the probability of the intersection of 2 sets. And now we want an expression about the probability of the intersection of more than 2 sets. Okay, so that term is here. And we want to express that in, in terms of the probability of the individual sets, and then we have those terms there. Okay, so let's bring this term of interest here, the probability of the intersection, to the right side. To the right side. So we have the probability of A1 intersection with A2. I'm sorry, I wrote union. A1 intersection with A2, intersection with so on and so forth, intersection with AN. So if that's on the right side, then this will be greater than or equal than 1 that's right, minus and we have now this expression here. And what is its sign? So again, we have p is on the right side, so then this needs to go to the left side, and so it'll be right here. Summation I goes from 1 to n of 1 minus the probability of ai. Okay, so need to make some room because it's not looking so nice over there anymore. Okay, so let's unpack what we have here. So on the left side we have the probability of a1 union with a2, so on, union with an is greater than or equal to 1 minus, so the sum, if we sum 1 n times, that's just going to be n, and then what we're left with is the sum as I goes from 1 to n of the probability of ai. Okay, and so now we just wrap this up. This probability must be greater than or equal than what? Well, here in the Bonferroni we had an expression first about the probabilities, and we got a minus and a minus, which will make the sign in front of that summation positive. So we'll write that term first. The sum from 1 to n of the probability of ai. And let's see, and then we were subtracting something here, so let's do a minus. So what do we have left? So what we have left is n minus 1, right? Yeah. Okay, so let's see now. If n is 2, and if we're looking at this, expression here, plug 2 for n, then we get that the probability of the intersection of a1 and a2 is greater than or equal than probability of a1 plus probability of a2 minus what? So if n is 2, n minus 1 is 1, so then we're subtracting 1, and that's exactly the Bonferroni inequality. So we've proven that by starting with Boole's inequality, we were able to show a more general version of the Bonferroni inequality. So pretty cool. But you know, let's not forget kind of the whole point of this subsection on the calculus of probabilities. The whole point was to expand the knowledge that we should have in our minds of what it means that a function is a probability function. Immediately we know only that the 3 axioms are true, but we've been showing in this section all these other results that are immediately true about that probability function, and it's, as you can see, there are quite a few results. Okay, so that's it for this section on the calculus of probabilities, and next we'll move to on this subsection. Next we'll move to subsections 1 to 3 and 1 to 4 on counting and enumerating outcomes. Okay, obviously I'm a big fan of this textbook. You know, this is why I decided to spend so much time with it. But I don't think this subsection 1 to 3 counting is motivated enough. The authors just jump into a bunch of counting, but I think in the student's mind there's the question of like, wait, well, what happened? How do we jump from looking at probability functions to now just doing a bunch of counting? The motivation is provided by the authors, but it's provided in subsection 1 to 4. So I'm just going to bring that to the front here. So the motivation is just a revisiting of something we've already seen. So you recall that we looked at how we can construct a valid probability function from valid probabilities assigned to the elementary outcomes. So if we had A be any event and P a probability function, we know that we can think of A as the union of its constituent elementary outcomes. So we could write it as probability of let's make it clear that the sample space here is finite, and it consists of the outcomes S1, S2, S3, and so on until Sn. Okay, so now we want to decompose this event A and write it as a union of the elementary outcomes. So the set consisting of elementary outcome S1, unioned. So the only thing here is that we want to now include here only the outcomes that are included in event A. So let's just take a little example. So if we roll the die, we know it has 6 sides, and so these outcomes are numbered 1 through 6. That's our sample space for rolling the die. And suppose that we're interested in the event that we roll a 3, 4, or 5. We'll call this event A. Event A can be seen as the union of 3 elementary outcomes, 3, 4, and 5, and elementary outcomes are pairwise disjoint by definition. Okay, so I wrote here S1, but we don't know that S1 is an A. So right, in this example I wrote here if this is S1, S1 is not an A. So we want to write that A is a union of some elementary outcomes. So we'll need to use some letters. So let's say that the first one we will call J, unioned with maybe SK, and then unioned, and so on and so forth. We'll give a different letter for each outcome, and maybe at the end here there's an S, W, so the notation isn't that great, but you see what I'm trying to do. We're trying to decompose the event A as the union of outcomes. Okay, but which outcomes? Only the ones that are elements of A. So there's a better way to write this, right? So this is very clumsy notation, so we can write it as the probability of the union of sets consisting of elementary outcomes S of, let's say, J, where these J's are such that Sj is an element of A. So what we wrote here is the probability of the union of sets consisting of outcomes Sj, where J is such that Sj is an element of A. And notice that J here doesn't play any role by itself, it's Sj that we're interested in, and so I can get rid of the J there in general, and so we're taking this union over the set of Sj that are elements of A. Okay, and so by definition, elementary outcomes are pairwise disjoint, and then by axiom 3, the probability of the union of pairwise disjoint sets is the sum of the individual probabilities. So we had J. And the sum is over all Sj elements of event A. Okay, so that looks good, and now so notice that now we're basically wondering, well, how many elementary outcomes are there in event A? And we're obviously wondering now if these outcomes are equally likely. So in these two subsections, 1, 2, 3, 1, 2, 4, we will work exclusively with finite sample spaces. You see, this is finite, it has n elements, and only with the case where the outcomes are all equally likely. So these n outcomes are taken to be equally likely. Okay, so then if we have n outcomes and they're all equally likely, and recall that the probability of each outcome and the sum of the probabilities must be 1, right? So essentially we have that P1 corresponds to that, plus P2 and so on, plus Pn. The sum is 1, and they're all equal to each other. P1 is equal to P2, so on, equal to Pn. Therefore, each of these Pi's must be 1 over n. Right. So then we can plug that in here and rewrite the sum as the sum of 1 over n, and we're summing it over however many outcomes there are in the event A. So if we had a sample space that had let's see what we got here, 16 outcomes, and we were interested, and they're all equally likely, and we're interested in the probability of this event that contains 6 outcomes, well then we're going to sum, in this case we're going to sum this 1 over n 6 times, right, because that's the probability of one outcome, and we have 6 of those, so I'm going to sum this 6 times. We'll get 6 over n. And notice that if we were interested now in this outcome, in this event instead, which also consists of 6 outcomes, it'll have the same probability because all the outcomes are equally likely. So then it's just the number of outcomes in the event that matters. And if we were interested instead in this event over here that contains only 2 outcomes, then we would sum this 1 over n just 2 times, and we would get 2 over n. So notice that what we have in the numerator is the number of outcomes favorable to the event we're studying, or number of outcomes included in the event A, and what we have in the denominator is the number of outcomes in the entire sample space. So then what we can do is we can write now that this sum here is essentially a ratio of 2 numbers. How many outcomes, number of outcomes there are in event A of interest, and in the denominator, number of outcomes in the sample space. So all that's left to do is to count for a particular event how many outcomes there are favorable to that event, and we'll count how many outcomes there are in total in the sample space, divide one by the other, and we'll get our probability of A. So notice that calculating probability of events in this case, when we have finite sample space and all the outcomes are equally likely just becomes a counting exercise. So hence this subsection now, 1, 2, 3 on counting. Notice one thing, we have not introduced a new definition of probability. Sometimes this here is referred to as the naive definition of probability. It's as if, oh, look, there's a new definition of probability. No, we have not introduced a new definition of probability. We have used the same axiomatic definition of probability, but in the case when the outcomes are equally likely and the sample space is countable, that axiomatic definition reduces itself to this ratio of two numbers, the outcomes, number of outcomes in A divided by the number of outcomes in the sample space, and it becomes a counting exercise. Same axiomatic definition though, so not a new definition. So what I think is important here is to understand that there are these 4 ways of sampling k elements out of n element, and understanding whatever question you have in front of you to which of these 4 it maps. I think that's the part that's important. So there are formulas for each of these, but let's just flush out one example first, and then we'll look at the formulas. So imagine that we have 4 elements, A, B, C, and D. So our n is 4, there are 4 elements to choose from, and we want 2 of them. So our k is 2. And we want to sample with replacement and in an ordered fashion. So let's see what that means. So let me first write out the sample space here. So what are the possible outcomes? AB, AC, AD, BC, BD, CD. So that's 6. So the fact that we are sampling in an ordered fashion means that AB is different from BA. Therefore, we have to also include here the ones corresponding to the above, but just reordered. DB, so I'm just reordering the outcomes from above. Okay, so we had a 6 there, a 6 here, 6 here, and there are a few more because now we're sampling with replacement. So think of what that means. Basically there's some sort of bowl, and there are 4 circles here, A, B, C, D, and so we draw one of these balls here. So let's say we draw an A, so A is out. Now sampling with replacement means that before we do the next draw, we put the first one back. So then AA is a possible outcome when we're sampling with replacement, as is BB, CC, and DD. Okay, so we got 4 here. 6, 6, and 4 for a total of 16. So it looks like this number here is going to be 16 when we're sampling with the replacement in an ordered fashion. Okay, now what if we were sampling without replacement and in an ordered fashion? So if we did without replacement, let's see, so without replacement just means that we cannot have these AA, BB, CC, DD, right? Because once A is drawn, it stays out. So A is not put back, so you cannot have AA. You cannot have the same one repeat. Okay, so then it's just these 4 that will go away. So then we would have 12 here. Okay. Now what if we sampled with replacement and but in well, no, let's do that one last. So let's do without replacement and unordered. Okay, well, the fact that we're sampling in an unordered fashion means that BA is no different than AB, and same with CA, DA, right? So these 6 here will not be included. So let me just delete that and draw a line through them. Okay. Okay, and we're sampling here without replacement, so that means that we cannot have repeats either. So then we would have 6 here. Okay, and only one left now. We need to sample. With replacement and unordered. So with replacement and unordered, so notice that the unordered means that these 6 here are not counted as separate outcomes, so therefore they're not in the sample space. But with replacement means that these 4 here at the bottom are okay. So we got the 6 plus 4 for a total of 10. Okay, so I think it's important to just understand what do we mean by with replacement, what do we mean by ordered, unordered, and I think that this minimal example delivers that. Then the next thing is to realize that I mean, in this case we picked n to be 4 and we picked k to be 2, and so we got these numbers 16, 12, 10, 6, and we could do it by just enumerating all the possible outcomes in each of those 4 experiments. But when n and k become a lot larger, it will be here until tomorrow if we listed out the entire sample space. So then we need more general formulas. So this 16, so more generally, how do we do that? Okay, well, let's remind ourselves what that is. So what's the sample space for it? So we're sampling in an ordered fashion and with replacement, so all 16 are included. Okay, and so where do we get that 16 from? Well, we're sampling our k's too, so you can picture as having two squares, and in the first one, any of the 4 is a candidate, right? And because we're sampling now with replacement, so we put one back. After we draw it, it's available. All of them are available for the second draw. So that 16 is really just the product of 4 and 4, or that's 4 to the second power. More generally, that's n to the power of k. And so that's the formula for counting with replacement and ordered. That's all we need to say there. Now if we're looking at without replacement and ordered, and so let's go to this one next. So let's identify the sample space for that experiment. So since it's without replacement, these 4 are not participating, but ordered, so that these 2 are okay. So we should have 12. And where does that 12 come from? Again, this one is very simple. Because k is 2, we have 2 boxes, 4 in the first one because any of the 4 can be picked into the first position, but then only 3 in the second position because whichever one was picked to be in the first position cannot appear again because we cannot have the repeats, right? The AA, BB, CC, DD are not possible outcomes here. So then it's just 4 times 3, and more generally the formula is n times n minus 1 and so on times n minus k plus 1. So let's see, if k is 2, we want this term to be n minus 1, is it? Yes, if k is 2, we get n minus 2 plus 1, that's n minus 1. If k is 3, we want this term to be n minus 2. So if k is 3, we get n minus 3 plus 1, so that's n minus 2. So yeah, this is the formula. And you may recognize this as a ratio of two factorials, in particular n factorial over n minus k factorial. Right, when we divide those through by n minus k factorial, what we get in the numerator is exactly this expression. Okay, and that's the formula that I'll plug in here. So that's n factorial over n minus k factorial. Okay, and we can test it. In our case here, we had n be 4 and k is 2, so we have 4 factorial over 4 minus 2 factorial, and that's 4 factorial over 2 factorial, and that's 3 times 4, which is 12. Okay, so that checks out. Okay, that's all that I wanted to cover for that one. So next is the case in which we're sampling without replacement and unordered. So let's take a look at that. Okay, so first, what's the sample space? What's the sample space in this case? Let's see. So without replacement, these are not there. Unordered, we're doing without replacement and unordered, yes. Unordered, so then these guys are not there. So it's just the 6. Okay. Okay, so this is a very important way of counting. The formula that's going to go in there is n choose k, which can also be written as n factorial over n minus k factorial times k factorial. It can be motivated in many different ways. I will just briefly maybe mention Pascal's triangle here, if you've forgotten it. But these coefficients come directly from Pascal's triangle, which is built like this, where you start with a 1 on top and then a row with 2 1s, and then after that you obtain the elements by summing the 2 above it. So this is a 3 here, this is a 3 and a 1, 1, 4, 6, 4, 1, and so on. And these rows are numbered, so this is n0, n1, this is n2, n3, n4, and these positions should be considered as numbered, and the first element is always in position 0, 0, 1, position 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4. So, if we were interested in, again, 4 choose 2, so that means, so we got our n choose k, so then we're picking n to be 4, so we'll be looking in the 4th row, and we're picking k to be 2, so then we're looking at the one with index 2, and that will be 6. And that's what we just worked out. And so these numbers in Pascal's triangle, they're also known as binomial coefficients, and that comes from the binomial expansion. So if we had x plus y to the power of 0, well, that's 1. X plus y to the power of 1, well, that's x plus y. If we had x plus y to the second power, then we got x squared plus 2xy plus y squared. And if we had x plus y to the third power, then we'd get x cubed plus 3x squared y plus 3x y squared plus y cubed, and so on. So we'll notice that the coefficients here are coming directly from Pascal's triangle. This one here is that one there at the top of the triangle. This has a 1 and 1, and so these are those two ones. Okay, there's a 1 here, 2 and a 1. That's the second row of Pascal's triangle. And then here there's a 1, 3, 3, 1, and that's the fourth row of Pascal's, the third row of Pascal's triangle. Okay, so okay, but what's the connection with the whole, ordering, sampling without replacement in an unordered fashion? So we can get a little bit of that intuition from doing this multiplication out. So x plus y cubed is just x plus y times x plus y 3 times, right? This 3 times is an n of 3. I'm going to try to build the connections to sampling without replacement in an unordered fashion. Okay, then let's multiply the first 2 out. We get x squared plus xy plus yx. Okay, but yx and xy are the same, and that's a connection to the unordered sampling. Okay, so I will just write it as yx then, plus y squared times x plus y. And if we multiply this out, so first I multiply everything by x, we get x cubed plus x squared y plus x squared y plus x y squared plus, now the next row, x squared y plus x y squared plus x y squared plus y cubed. Okay, so what do we have now? Well, let's collect some terms. So how many x squared y's do we have? 1, 2, 3. Okay, and how many xy squared do we have? 1, 2, 3. Okay, and then so we see now where this comes from. And the part I think that I wanted to mention here is, let me erase here, make a little room. So let's look again at what we have here. So this first term, I'm going to write it as x cubed times y to the power 0. The second term as, and so we have the 3, and then x squared y to the power 1. The third term as 3 times x to the power 1, y to the power 2. And the third one as x to the power 0 and y to the power 3. And notice that the powers always add up to 3 in each of these monomials, you call them. Okay, so then the generic term can be written as x to the power of n, right, n is 3, minus k times y to the power of k. That's the generic term. And then, so where do these numbers come from then? The 1 basically here, the 3, and the 1. Well, we just count how many of these guys we have. So then, it's a question of, okay, well, how many will we have? And that is a question of, well, how are these ky's built? And the number of ways to choose which of these factors out of n contribute a y, so that number is n choose k. So there's a little bit of intuition here, not a ton, and we've already talked about the unordered, and we've seen it here, and and it's without replacement, right? Because as we are thinking about which k factors out of n contribute a y, the same factor cannot contribute y more than once. So now I think we've closed the loop there. So we've seen why it's without replacement, why it's unordered, and we've seen how this is a counting exercise. Okay, but in the end we just need the formula really, and it's that n choose k is just n factorial over n minus k factorial, k factorial. Okay, so we have only one more counting case left, so let's take a look at that. This one is the hardest. So the one that's left is with replacement and unordered. So okay, let's find the sample space for it. So with the replacement and unordered. So unordered means that these 6 are not different outcomes than the 6 above, but with replacement means that these 4 at the bottom are okay. So these 6 are okay, the 4 are okay, for a total of 10. Okay, but if n and k were larger, how would we count the number of valid outcomes? So there's a pretty brilliant approach here that I personally would have never come up with, but somebody who must have thought about this for a long time came up with it. The idea here is to move from counting with the replacement in an unordered fashion to a place where order does matter, because we have we have tools that we can use there. Okay, so what's the idea? I mean, the idea is to think about what this unordered means. When we can sample with replacement, it basically means that all we're keeping track of is how many of each have you picked. So in this case here we have A, B, C, D. We have 4 elements. So if we pick A, B, that outcome, that just says take A once, B once, and C and D 0 times. And if we look at this outcome CC, that one says take A 0 times, B 0 times, C 2 times, and D 0 times. Okay, and that's it's interesting. So that kind of looks like it solves for some equation, x1 plus x2 plus x3 plus x4, where it looks like the sum is of these guys is always 2, right? The sum is 2 here, is 2 here, and this 2 is just the k. Okay, so basically we're looking for how many non-negative integer solutions to this equation do we have, and it's not clear how we would count those, but a brilliant observation was made by somebody, and that's that we can transform this question into one that's a lot simpler by noticing that we can think of as having a wall here, another wall here, and another wall here, and instead of putting a 1, we'll put an M for marker, and and each wall will be denoted by a W. So then this first outcome here maps to there being a marker because there's this 1, then there's a wall, this wall, then there's another marker, then there's another wall, then another wall, and that's it. And so notice that each of these is going to have 2 M's and 3 W's. Okay, so this one maps to what? Well, there's a wall, wall, then 2 markers because of this 2 here, and wall. Okay, so now by sheer magic, so we've mapped those the outcomes here on the left, which were kind of cryptic, to these ones on the right, which look like permutations, and they are, so if we go back to like problems that we probably all seen before, such as if you had the word A, B, 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 and not a word, but you had these letters C, D, E. How many ways are there to permute this, these letters? You may remember the way to do that is we count how many letters do we have. I got 3, 6, 8. So we have 8 factorial, but we have to, because these A's are indistinguishable from each other and the B's are indistinguishable from each other, we have to divide by each letter that repeats. So this 2 factorial is because there are 2 A's, and then there's a 3 factorial because there's those 3 B's. And so this here would give us the number of ways to permute these letters. And in our case, we're looking essentially at how many ways are there to permute the letters 2 M's and 3 W's. Well, by the same method, we count how many letters we have, 5, so it's 5 factorial, but we have to divide by 2 factorial because there are 2 M's, and 3 factorial because there are 3 W's. And so what would we get? Divide through by 3 factorial, we get 4 times 5, and the numerator 2 in the denominator for a total of 10, which matches the 10 that we got here. So that's encouraging. So essentially that is the answer. Not a ton of added value, I think, in going in this direction, but hope it's useful nonetheless. The book does cover this, but at the end of the day, we just need the formula, and the formula here is n plus k minus 1, choose k. Yeah, and that's it. So one last or two more notes here and we'll close. So in this table, so there are 4 ways of sampling, right? And so the sampling with replacement and ordered is always going to give us the largest number of the 4. Sampling without replacement and unordered is always going to give us the smallest number of the 4. And the other 2 will be in between, and the rank order of the other 2 will change depending on the values of n and k. So that's the first thing. Oh, I did want to do some exercises where we just recognize which one, which counting method applies. Okay, let's look at question number 1. So we're at the ice cream store and they have 8 ice cream flavors. And so we're going to build an ice cream, so there's going to be a cone, and then we're going to put 3 scoops of ice cream here. And so if we put chocolate, vanilla, strawberry, that's a different ice cream than if we put strawberry on top, chocolate second, and vanilla at the bottom. So order matters, and it's with replacement, because you certainly can order the same flavor. You can have 3 scoops of strawberry. Okay, so how many different ice creams can we have? We need to see which of these 4 scenarios are we in. So we're sampling with replacement, because the same flavor can be repeated, in an ordered fashion, because strawberry, vanilla, chocolate is different than chocolate, vanilla, strawberry. So therefore, that puts us in row 1, column 1. Okay, our n is 8, because there are 8 ice cream flavors. Our k is 3. We're trying to pick 3 of them. So then the answer will be given by 8 to the 3rd power. So that's our answer here. Okay, question 2. Now let's say that we're at the smoothie store, and there are 8 fruits that we can use in our smoothie. But we know how a smoothie works. You just pick the 3 fruits, and then they're going to be all mixed in. So the order doesn't matter. Order doesn't matter. But you can definitely pick the same fruit. You can pick 3 servings of strawberry. So then it's with replacement, because we can pick 3 servings of strawberry, but it's unordered, right? Because they're going to be mixed anyway. So then the formula is this n plus k minus 1, choose k. And given our n is 8 and k is 3, the answer here would be 10, choose 3. Okay, that's that one. Now if we had a question where we are picking, we have 8 students, and we need to pick 3 of them to serve on a committee of 3. So the same person cannot serve, cannot be represented 3 times on a committee. Therefore, it's without replacement. Okay, and then the order doesn't matter, because we didn't say anything. We didn't say there's going to be a president of the committee, vice president of the committee, and a treasurer. We just said a committee, so it's sort of like they're mixed in there. Okay, so then it's without replacement, and order doesn't matter. So then we're in row 2, column 2. So the answer will be given by n choose k, and that's just 8 choose 3. And now if we had instead 8 students being picked for, say, student government, and there are 3 positions here. There's a position of president, vice president, and treasurer of the student government. How many different ways can we pick 3 students here? Well, it's without repetition, because the same person cannot be the president, vice president, and the treasurer at the same time. And it's ordered, because we're picking somebody to be president. So if John is president and 2 other people are vice president, treasurer, that's a different arrangement than if John is the treasurer and the other 2 people are president, vice president. So, okay, so then we're in this case where we're picking without replacement and in an ordered way. So then the formula we need is this one, and with n being 8, it's basically 8 factorial over 8 minus 3 factorial, so that's 8 factorial over 5 factorial, and that's 6 times 7 times 8. Okay, so we've seen an example of each of these sampling techniques, and so now kind of how does this relate to probabilities? Again, going back, we're going to do a counting exercise in the numerator, counting exercise in the denominator. In the numerator, we're counting the number of outcomes in the event A, and the denominator, we're counting the number of outcomes in the sample space. We divide those through, and we get a probability of event A. So that's it for these two subsections, and that's it for this section on probability theory. Yep, thank you for listening, and I'll see you in the next section.